Today, I'd like to talk about the derivatives of these vector-valued functions that we've started looking at. It might be helpful to remember what went on in the first semester. I'm going to have some function, f, and its graph described by y equal f of x. I'm going to pick some particular spot on that graph with x-coordinate c, y-coordinate f of c, and the question that you solved back in the first semester of calculus was this one. We want to find the slope of the tangent line, the slope of the straight line that touches the graph at x equals c and has the same direction as the graph at c. The idea was to take another point on the curve by increasing the x-coordinate by an amount delta x. Therefore, the new point is c plus delta x, f evaluated at c plus delta x. This is called a secant line, and the thought is that if delta x is not very big, then the slope of the secant line should approximately be the slope of the tangent line. The change in x-coordinate is delta x. The change in y-coordinate is the difference of the two function values. And to make this estimate of the slope of the tangent line better and then perfect, you take the limit as delta x tends to 0. You look at the slopes of such secant lines as this point is allowed to slide down the curve and get very close to the point you're actually interested in. We called that limit, if it exists, the value of the derivative at x equals c. Shortly after that, you developed a big bag of tricks and then didn't worry so much about the limit definition anymore. We're going to do something just like this with the vector-valued functions, except our function values will not be numbers anymore. At some particular t value, t equals c, I'll draw in the vector that goes with that. Let the t variable increase by an amount delta t, and I'll draw in the vector that goes with that t value as well. If r of t is f of ti plus g of tj plus h of tk, where f, g, and h are ordinary real number valued functions of t, we're going to define the derivative one component at a time. If all three of those derivatives make sense for a certain t value, we will call that the derivative of r evaluated at that t value. As an example of this, you could think of r of t as being t cubed I plus t squared j. Differentiating one slot at a time, r prime of t is 3 times t squared I plus 2 times t j. For a given t value, this will be a vector that tells me the direction that the curve is going in, except when it doesn't, which we'll get to shortly. As another example, I'm going to look at one of our prior vector-valued functions. If you'll remember, this is a circle with radius 5 centered at the origin. What I'd like to do is, I'd like to calculate for several different t values the r function and also its derivative. If t is 0, then r is going to be 5 cosine 0 in the first slot and 5 sine of 0 in the second one. That'll just be x equals 5, y equals 0. If t is equal to pi over 2, the cosine will be 0 and the sine will be 1. If t is equal to pi, the x-coordinate will be negative 5 and the y-coordinate will be 0. And if t is 2 pi over 3, then the x-coordinate will be 0 and the y-coordinate will be negative 5. We are traveling around a circle in a counterclockwise direction. The derivative of this vector-valued function is negative 5 sine ti plus 5 cosine tj. I want to plot these derivative values. Instead of drawing the vectors with their initial points at the origin, I'm going to draw them at the corresponding endpoint of the vector values. Since sine of 0 is 0 and cosine of 0 is 1, r prime at 0 is 0 times I plus 5 times j. It's a vector that points in the positive vertical direction with length 5. I'm going to draw that in with its initial point at the location of the vector value. At t equals 0, the direction the curve is traveling in is this direction. The significance of the length will come out in a little while. Doing the same at t equal pi over 2, my answer is negative 5i plus 0j. Negative 5i plus 0j points to the left horizontally. The sine of pi radians is 0. Cosine of pi is negative 1. The derivative is 0i minus 5j, which points vertically in the negative y direction. It doesn't take much of an imagination to guess what the last one is going to do, but we'll do it for completeness sake anyway. In each case, the vector points along the direction that the curve is traveling in at that particular point on the graph. It is a tangent vector. In the first semester, we often wanted a derivative to be 0. For example, when we were doing maximum or minimum problems or finding inflection points, it turns out that what we want to happen in Calc 1 is what we don't want to have happen now. If I were to tell you a value for one of these functions, say that r evaluated at 3 is the vector 1, 2, this tells me the endpoint of the vector that goes with that t value, or if t is time and I'm actually thinking about the component functions as being coordinates, that is literally x equal 1, y equal 2, the function value by itself tells me where I'm located at, but it says nothing about the state of motion, if I'm thinking of this as time and position. But if I knew the value of the derivative at t equal 3, I would know something else. I would know the direction that this path is taking right at the place where t is equal to 3 is pointing 1 unit in the negative x direction and 1 unit in the positive y direction. That would tell me that close to this particular point, the point where t is equal to 3, my graph must look like this. It's perfectly all right if one of the components of the derivative is 0. If r prime at 3 were the vector 0, 2, that would mean right at that point on the graph, there is no horizontal motion, but you're moving upwards in the positive y direction. Likewise, it would be all right if the second component of the derivative were 0 and the first was not. This would tell me that right at t equal 3, I'm passing through this point 1, 2 in a horizontal direction. It doesn't take a rocket scientist to see where the discussion is headed. If r evaluated at 3 was 1, 2, sum at this point again, and the derivative at t equal 3 evaluates to 0, 0, the 0 vector, then this is not good. This doesn't tell me which direction I should be going in if I want to stay on the curve. As a result, this is the desirable situation. The derivative makes sense and is not 0. because if it is, it doesn't tell you anything. For reasons that'll become clear shortly, I'm going to be official and say that a curve is a set of equations that give you x, y, and z if you're in 3 dimensions, or described by some specific vector-valued function together with the graph. If I have the same picture, but I got it using different equations, the graphs are the same, but technically the curves aren't. This seems like a really picky distinction, but we'll see in a little bit. In many formal statements of theorems, they start off with, let so-and-so be a smooth curve. So we need to be clear on what that means. A curve, which is a set of equations and a picture, or a vector-valued function and a picture, is smooth on an interval if two things are true. Firstly, for any t you pick in the interval, you can evaluate the derivative. Also, there is no place in the interval where the derivative comes up the zero vector. The reason that we want the derivative to exist is that typically it tells us the tangential direction. The reason we don't want it to be zero is that's the one situation where the derivative makes sense but doesn't tell us anything. So smooth curves are sort of generically the easy ones to think about. As an example of this, imagine that somebody had equations for x and y in terms of t, or a vector-valued function, and that you eliminated the parameter. When the dust finally settled, the relationship between x and y was just that x equals y, which is an unbroken, continuous straight line of slope 1 that passes through the origin. And then someone asks, is that a smooth curve or not? The knee-jerk response is to say yes, because what could be smoother and more continuous than a straight line? The real answer, though, is we can't tell. For example, think of r equals t times I plus t times j. If you eliminate the parameter, that does give you y equal x. The derivative is the constant vector I plus j, which is good on two counts. Firstly, the derivative makes sense no matter what the t value is, and even better, this derivative is never the zero vector. So this curve, which is this vector-valued function together with the picture, is smooth on all intervals of numbers. This is the international symbol of mathematical happiness. But there's more to it. As t varies over the real numbers, t cubed does so as well. There are t numbers that when you cube them will give you positive, negative, or zero answers back. So we're definitely not leaving anything out here. This says that x is t cubed, and that says that y is also t cubed. That says that y and x are the same thing. The graph is the same. If I want to investigate the smoothness of this, I need to look at its derivative. The derivative makes sense no matter what t is, but if t is 0, the derivative is going to come up 0. From a technical perspective, this is not a smooth curve on any interval of t numbers that includes t equals 0. If you're looking at the interval of t numbers from 1 to 7, though, it is smooth on that interval. It's smooth on the interval from t equals negative 10 to t equals negative 2, but it isn't smooth on the interval from t equals negative 1 to t equals 1, because 0 is in there. The punchline for this is, if I just show you the picture and I ask you if that represents a smooth curve or not, it's not a reasonable question. You can't tell. It might be like this, or it might be like that. In ordinary calculus, we had a bunch of procedures like the product rule, the quotient rule, the chain rule, and so on and so forth. It turns out that there are very similar things for these vector value functions. Generally speaking, what I'm going to do is wait until I need one of these properties and then show that it's true right before I use it. But I want to look at this one in particular. I'm going to have two vector-valued functions, r and u. I'm going to form the dot product of those two things, which will be a function that gives you numbers back for answers. I want to take the derivative of the product and see if there's some sort of product rule-like thing. In what I'm about to write down, I'm going to omit the of t's just to save writing. I'll put them back in at the end. I'll call the components of r a and b. A and b are ordinary functions of t, as are c and d. I'm working this in 2 dimensions. The argument for 3 is exactly the same. Since a times c and b times d are just ordinary products of regular old number functions, we can use the product rule on them individually. Then the thing to observe is some of these terms that I've written down here have components of the original r and others don't. So we'll group things that are similar looking together. If you look at the first 2 terms, that's the dot product of vector AB with vector C prime D prime. The second term is the dot product of the vector A prime B prime with vector CD. But that's equal to r dot u prime plus r prime dot u. I wrote these backwards. That's perfectly okay because a dot product is commutative. This shows me that the derivative of r dot u is the first function dot product with the derivative of the second one plus the derivative of the first one dot product with the first function. It's just like the product rule from Calculus 1, except these are not number functions. These are vectors. Now, I want to be even more transparent about what I'm up to than I have been. I'm going to think of having a vector-valued function in 2-dimensional space. T now, for this problem, is literally time since some specified starting time. X of t is going to be the x-coordinate of some object that we're looking at, and y is going to be the y-coordinate. I'm going to start at some particular t value, and then increase the t value by an amount delta t. If I look at a very small bit of my vector-valued function, the path looks more or less like a straight line. And the smaller that I make these pieces, the better that will be, assuming the function is smooth. For something like that, I can think about the distance traveled during this little interval of time values. I can think of it using the Pythagorean theorem. The average speed is the distance covered divided by how much time it took. On the bottom of that fraction, I could write delta t as the square root of delta t squared, and then combine the square roots into one expression. This is just the average speed, though. If I was interested in the speed at some particular point, say the place I started at, I would let the delta t go to 0, The limit of delta x over delta t is dx dt, and likewise the other term is dy dt squared. This gives me a formula for the instantaneous speed as the object travels along its path. The connection that I want to make is this. Take the derivative of the r function, and then think about the magnitude of that vector. You would take dx dt, square it, square dy dt, add those together, and do the square root, which is the same thing as that. The magnitude of r prime in this interpretation is the instantaneous speed of the object. For this reason, r prime is often given another name. It's often called the velocity vector and symbolized with a v. We'll talk more about that real soon now. In the meantime, I hope everyone's having a good day, and I'll talk to you again soon.